Hello everyone, my name is Dhyey Dave from third year BSMS Physics. Today I'll be presenting my project on galaxy stellar mass estimation using convolutional neural networks. So this project aims to estimate the total mass of the galaxies using CNNs which are trained on astronomical images. So instead of relying on traditional spectroscopic methods, here we are using deep learning model to identify patterns from the galaxy features or the galaxy morphology and estimate its stellar mass. So to begin with, let's understand the foundations. What is stellar mass? It is this total mass contained in the stars within a galaxy. It is usually expressed in the units uh, of log m star by m dot, where m star is the mass of the star and m dot is the sun's mass. The classical approach for this is the photometric spectral energy distribution fitting uh, using the stellar population synthesis model. In this approach, the observed light from the galaxy is modeled using stellar population models which stimulate how the population of stars of different ages and metallicities contribute to the galaxy's overall light. The central quantity in this is the mass to light ratio, which is essentially the galaxy, how the links galaxy's brightness to its stellar mass. But this ratio is very sensitive to factors like the stellar age, metallicity, and the dust content. So this is where CNNs come into picture. The key insight here is that the galaxy morphology, that is its visible structure, encodes physical information. Processes like mergers or star formation not only change the galaxy's mass but also its appearance. For example, the massive galaxies or the early type galaxies are elliptical, red and quiescent. There is not much merger or formation events occur, whereas the low mass galaxies are spiral, blue, and star formation events occur in them. The CNNs capture these patterns like axis ratio and other features, and it learns the mapping from the pixel space of the image to the stellar mass values. Hence, our goal here is to provide a fast, robust mass estimate, particularly valuable for large imaging surveys like upcoming surveys of the Vera-C-Rubin Observatory, LSST, etc., where the SAD fitting technique is computationally expensive. So the task, our task here is basically a regression task, which is used to predict the continuous stellar mass value. The success of this model is highly dependent on the quality and the integrity of the training data and the mass labels. Our input data here is the SDSS or the Sloan Digital Sky Survey multi-band image cutouts in the red, green and blue image channels as shown here. These cutouts are pre-processed for uniform size and normalization. Our target labels are derived from the Firefly SAD fitting pipeline, which means these are already derived using the SAD method and used as a reference for training. Our objective function unit uses the mean square error for minimizing loss, and the performance metric is evaluated using the root mean squared error and the R square score. So the theory takeaways are that when applying deep learning methods to scientific data, particularly astronomy, the challenge isn't just accuracy, it's also generalization. We want the model to learn real physical correlations from the dataset. For this, we use three techniques. Data invariances, that is, we introduce image transformations, that is noise, into the dataset by rotating our images. So this data augmentation technique ensures that these small transformations during training make the network invariant to such changes. Second, sorry. Second is the regularization technique. Techniques like dropout and L2 regularization prevent the network from memorizing features from the training data. Third is the validation discipline. That is, the training, validation, and test data sets are strictly separate. This ensures the model's true accuracy on unseen data. So let's dive into the code. Uh, the structure, the flow of the code is as follows. We first start with data acquisition, where the raw catalog images are ingested. Next, we move to pre-processing, where normalization, resizing, and assembly of input-output pair happens. And finally comes the model training. Uh, During our steps, we are defining artifacts like the catalog CSV files and the NPZ image files, which ensure that the data is stored clearly for future use. We are also saving the model with its weights, so we can directly import our model for future use. And for reproducibility, we are also ensuring a fixed random seed and version tracking for consistent results. So let's move to environment setup and data ingestion. We are using libraries like NumPy, Pandas, uh, AstroPy, and TensorFlow and scikit-learn. We are also using additional libraries like async.io, HTTP for ingesting data, which will be discussed later. We are making our working directories so that we can store data while running the code. This also serves as a checkpoint for during the data processing. So let's move on to data ingestion. Here we are converting the fits file to pandas data frame for easy data processing, and also we are filtering our mass column for positive mass values, and also to remove the null values. We are taking a sample of 10,000 images from the uh, dataset for our prototyping. Next comes the SDSS cutout acquisition. Here we are using a URL builder, which is so here we are using the SDSS Sky Server API, which basically is used to download the images from the SDSS server. Here we can input values like the array deck of the galaxy and parameters like the scale or the scaling of the images along with the size of the images required. Here the scaling of 0.396 is selected based on the uh, signal to noise ratio and other parameters of the SDSS telescope. So this is completely dependent on the instrument. Next comes our asynchronous downloader function. Uh, this downloads the images from the SDSS server asynchronously. Uh, so basically this is an optimized code for downloading images. Next comes the main function, which integrates the URL builder and the async downloader for downloading the images. Here we can define parameters like the batch size and the a number of images downloaded at once. Also, one more important point to note is the net async io.apply function. This is used in collab runtimes where multiple event loops are running at once. So if you want to run this code in Google Colab, you need to add this code snippet. So finally, when we run this function, the images are downloaded as the image path and the mass labels, and it's stored in our as a CSV file in our directory. So next, once the image is downloaded, we perform the visual sanity check. We pick up a sample of 25 images from our 10,000 images sample and check whether the images are proper with the mask labels properly centered. Once the data is downloaded, we move on to data pre-processing. This involves loading and resizing the images and also normalization uh, to ensure it is compatible by the CNN. After that, we divide our uh, data into the image array and our mask labels. So it's basically dividing into the features and the targets. And after that, the data set is, after processing, the data is stored in the NPZ format, which is basically a serialized data format to bypass reprocessing time in the future code. After this, the dataset is split into training, validation, and test datasets. The training is used for optimizing the model weight. Validation is used for hyperparameter tuning and also for the early stopping criteria. And the testing is used for the final uh, performance evaluation of the model. Here, the reproducibility is ensured by fixing a random seed so that the target variable is distributed consistently across all the three sets. Next up is normalization and data augmentation. Normalization basically adjusts the pixel values to match the requirements of the pre-trained ResNet backbone. So here we're using the pre-process input function uh, which scales the images in a way compatible to the ImageNet based model, which is our ResNet model. Then comes augmentation, where we are introducing noise through minor transformations and rotations so that our model is invariant to such changes in the future. Here we are using the principle that rotation does not change the mass of the galaxy. Then we are creating the data flows, which is basically the logical order to be followed by the data here that will be the normalization and the augmentation step. So we are defining this pipeline over here, which is the pre-processing as well as the augmentation pipeline, and for the test set, for the train set, as well as for the validation and the test set. And we are implementing this pipeline into the three sets using flow function. So next, let's discuss the model architecture. Our CNN backbone here is the ResNet 50, a deep residual network which is pre-trained on the ImageNet. The residual network, from which the ResNet name comes, it skips connections which helps maintain the gradient flow even in very deep architecture. This prevents the problem of vanishing a gradient. So initially during training, we freeze the lower levels which capture generic information like the edges and the textures. Later during fine tuning, we selectively unfreeze the upper layers uh, to adapt to the astronomical image features. We are also adding additional regression head like global average pooling, which converts the final convolutional feature map into a single vector by averaging the spatial dimensions. This reduces the parameters and prevents overfitting. Next, we are using regularization techniques like dropout. So dropout randomly deactivates the neurons during training to improve generalization. And we are also including the L2 regularization. It is essential in fully connected layers which learn the non-linear mappings from the extracted features to target values. So the L2 regularization penalizes the large weights and promotes smoother and stable learning. So these methods ensure there is no overfitting. We are also adding a single linear output for our regression. Since our model predicts a continuous value, that is the stellar mass, there is no activation function required as we are performing a regression task. So next comes the optimization and training controls. Here we are using the Adam optimization, which dynamically changes the learning rate to improve convergence. We are using the mean squared error as uh, for a loss function. Here we are implementing three callbacks. Early stopping, which uh, halts the training if the validation loss stops improving, and this method prevents overfitting. Secondly, we are using reduce LR on plateau. So it is designed to adapt how fast the model learns. When the validation loss stops improving for a few epochs, here we have set it as 2 epochs. The callback automatically lowers the learning rate by a factor of half. So this reducing the learning rate at this stage uh, helps the optimization make smaller steps and precise weight updates to the model. So this helps the model escape uh, flat regions and move to deeper minimum. And finally, we are using model checkpoint, which only saves the best weights. We are using the batch size, which is depends on the GPU available. Here we are using the batch size as 32, which is good enough for the system available. And the epochs, number of epochs is determined empirically on the basis of convergent trends and validation in the validation loss. So after all this, we run the model and let's move to the results obtained and the future work that can be done. We evaluate the model performance using the metrics R score, mean absolute error, and the root mean squared error. So here we can see that the R score is about 0.637 or 0.64, which means the model explains 64% variance, uh, which shows the good predictive power of the model. Next, we have an mean absolute error of about 0.322 decimal exponent. Dex is the unit decimal exponent, which means it is in the power of 10. So here we have an mean absolute error of 10 to the power 0.322, which is approximately 2, which is a good result. Uh, Here from the training curves, from the learning curves, we can see that there is no overfitting because both the validation and the training loss are decreasing simultaneously. Also, the predictions are unbiased because the residues are centered on zero. So the model is not over or under predicting. We can see the interpretations from the graphs uh, discussed in the previous slide. So the limits of this interpretation is that the systemic over and under prediction in specific regions, that is the bias patterns, is not clearly seen in the low luminosity galaxies. The heteroscedasticity, that is the prediction variance changes with the magnitude of the target label. The resolution and the image constraint, the image fidelity is limited to the SDSS cutout. It is basically how the images are available from the SDSS server. And the label noise, that is the uncertainty in the mask labels. For future work, uh, we can focus on improving the consistency and the quality of the input data streams. We can transition to the fully calibrated FITS files. That is, we can use the entire UGRIZ band for analysis. We can conduct rigorous calibration check to confirm that the prediction aligns with the observed frequencies. We can implement k-fold cross-validation to ensure model stability and prevent overfitting to a single train test split. And we can test our model on external dataset completely different from our downloaded dataset or downloaded sample. So how is this project different from already available work? This project utilizes real observational data from the Firefly value-added catalog, which is based on the SDSS DR17 data release. It has spectroscopically derived labels, which are in contrast to the projects which often rely on the simulational models and images, simulational images and labels. Second, this only validates on the available SDSS mask labels, whereas high-end research studies conduct benchmarking against ground truth or references from the simulation. We are only focusing on a single band input of 128 by 128 cutouts, whereas the research papers use multi-channel input and also about 224 by 224 or 256 cutouts. This is limited by the available resources. This project is designed for transparency and reducibility and hands-on learning, which is differing from the production-oriented or simulation-driven research application. It does not include advanced generalization strategies, but obviously it is there's a scope for future expansion in this. The model employs ResNet 50, which is a single pathway, while others explore complex multi-branch and attention-augmented deep learning frameworks. So concluding, this project highlights how machine learning enables us to view galaxies not just as images but as data-rich structures which reveal their evolutionary history. The CNNs allow us to quantify the unseen, that is, revealing the link between light, structure, and stellar mass. This approach marks a step forward towards autonomous astrophysics, where algorithms learn the cosmos much like the astronomers once did through observation. So, thank you for watching and listening. I hope this presentation offered insight into how artificial intelligence is transforming modern astronomy. Thank you.